In this video, we will deal with vectors, what they are, how to add them, subtract them, and scale them pictorially. These first few slides are pretty self-explanatory, so I won't bother reading them out word for word. The text is pretty easy to read. Just pause the video and take your time reading it. And so I'll be a bit more silent these first few slides. Still a bit of brief commentary. Most of the quantities we deal with in this course will be either scalars or vectors. Scalars need only a number with units to describe the quantity. For example, the mass of an object. If you say it has a mass of 3.5 kilograms, you don't need to say 3.5 kilograms up or 3.5 kilograms left. It's just 3.5 kilograms. It's a number with a unit. Some other examples are temperature, volume, density, and so forth. Vectors, however, not only have a magnitude, they also have a direction. Some examples are displacement, velocity, acceleration, and then in Physics 120 we'll see electric field, magnetic field, and so forth. Once again, to recap the important point, scalars just need a single number with units, sometimes, and vectors need both a magnitude, which would have units, and a direction. Pictorially, we represent a vector by an arrow. Okay, and the length of the arrow gives you its magnitude, and the direction is given by the direction of the arrow. And it points from the tail to its head. If I include a set of axes, it becomes a bit easier to define the direction. So in this case, theta here is the angle that the vector makes with the x-axis. So the idea is that you are typically given some fixed coordinate system, and you talk about the direction of the various vectors with respect to that coordinate system. So here you would say that v makes an angle theta with the positive x-axis. And again, just a reminder or note, this symbol here is the Greek letter theta and is often used for angles. The magnitude is given by the length of the vector. Notice that for the vector itself, I use, in this case, the letter v with a little arrow on top. The magnitude of the vector is just the letter without the arrow, or it is sometimes written as the symbol for the vector. So here we have v with the arrow on top between two vertical bars. So this is the operation of taking the magnitude of the vector. Remember that the magnitude is just a number with units. It does not have a direction. So you need both the magnitude and the angle or the direction to reconstruct the full vector. If we move a vector without changing its directional length, then we say that the vector is unchanged. So for example, these two vectors are the same. They both point in the same direction. They have the same length. So these are the same vector. It's just been displaced parallel to itself. This new vector is not the same. Okay, if we compare this new vector with the first one, we notice that they both point to the right, but the original one pointed right and up, whereas the new one points right and down. So it is clearly not pointing in the same direction. It has the same magnitude, it has the same length, but it is not the same vector. Now this new vector over here has the same length, and it is certainly parallel, or more precisely anti-parallel, to the first vector. But because it is anti-parallel, okay, it's not pointing in the same direction. This one is pointing right and up, this one is pointing left and down. So it is not the same vector, it is in fact the negative of the first vector, and we will see that in more detail later. Once again, to reiterate, if I have a vector, say A, it doesn't matter whether it is here, or even here, or here. These are all the same vector A. This is still A, still A, still A, still A. Whereas these vectors B and C are not the same as A because they do not have the same direction. There are two ways to add vectors. The first is the tail-to-head method, and the second is the parallelogram method. But you will see that the second parallelogram method is in fact just a slightly more complicated version of the tail-to-head method. So, vector addition proceeds as follows. If we want to add these two vectors, A and B, we put the tail of B at the head of A, right? So the head of A is where the arrowhead is, and we move B until its tail is at the tip of the arrowhead. And now we join the tail of A, which is free, to the head of B, which is free. And this is the sum A plus B. All right, it goes like that. Here's another example. We want to add this vector A and this vector C. Again, we'll have to move C until its tail is at the head of A. So in this case, they both lie along the same line, so they're overlapping. A here is still going all the way till here. You can see the little blue arrowhead over there, right? A is going all the way here, and then C takes you back along the same line, but not all the way, only up to here. And then the final result goes from the tail of A to the head of C. And so this now is A plus C. The parallelogram method basically uses the two vectors that you're trying to add to draw a parallelogram. So we move the vectors again so that the tail of B is at the head of A, and then we duplicate B and shift it and put it at this position so that the tails of the two vectors join up. Remember that just moving a vector without changing its directional length leaves it the same. So this vector B is the same as this vector B. Now we do the same to A. We just move it parallel to itself, and now you can see we have constructed a parallelogram. Right? It's a quadrilateral, there are four sides, and opposite sides are parallel to each other. And now the resultant, A plus B, is just this diagonal. Okay, how do you know which diagonal? Well, we can see that these two vectors, A and B, which we're trying to add, lie along these directions, and the resultant, the sum, will lie between them. But you can also see that this parallelogram method is just doubling up of the usual head to tail, or rather tail to head method. Because this triangle here is just the usual B being placed with its tail near the head of A, and then connecting the tail of A to the head of B. We can also scale a vector, all right, by multiplying it by a number. So in this case, if this is the original vector b, then keeping the direction the same, but doubling the length gives us the vector 2b. And this is known as scalar multiplication, because we are multiplying a vector by a scalar, which in this case is just 2. The number doesn't have to be positive. You can multiply your vector b by a negative number. So here, for example, we are multiplying it by negative 1.5. The effect of the minus sign is reversing the direction. So instead of going to the right and down, this vector now goes to the left and up. We have reversed the direction. That is the effect of the minus sign. And then the 1.5 scales the length. So you can see that this new vector is longer than the original vector. So this new vector is related to the old one, and this new vector is negative 1.5b. However, remember that the magnitude of a vector is always positive. So if I were to take the magnitude of this vector, this new vector, it would still be positive. But direction-wise, we can see that this is in the opposite direction to the original vector, and that is related to the minus sign. We can use this to subtract two vectors. If I want to subtract b from a, in other words, if I want to do a minus b, I first take b and multiply it by minus 1 to get minus b. And now I add minus b to a. So I have taken the minus b vector, I just moved it over here. And what did I do? I placed it so that its tail, the tail of the minus b vector, is at the head of a. So I'm using the tail to head method. And now the resultant is a plus minus b, or in other words, a minus b. Now we're going to talk about some of the properties of vector addition. First of all, it is commutative, which means that the order of addition doesn't matter. In other words, a plus b is the same as b plus a. The proof here, we've taken those two vectors a and b, and, well, it's not really a proof, it's an illustration. Here we are doing a first and then b. Here we are doing b first and then a. But in both cases, the final resultant vector c is the same, and you can see these are in fact the same vector. So it doesn't matter in which order you add them. Of course, that only is with regard to addition. Subtraction, obviously, a minus b is not the same as b minus a. Vector addition is also associative, which means that if you have more than one vector which you need to add, it doesn't matter whether you do d plus e and then f, or e plus f and then add d. So if these are d, e, and f, again we illustrate the associative nature of vector addition. Here I've constructed d plus e, so I've taken d and e and added them to construct d plus e. Then I brought f such that the tail of f is at the head of d plus e, and this is the resultant d plus e plus f. Now in the second case, I first do e plus f, so here's e and f, and this is e plus f. And then I do d plus e plus f. Right, so I put the d vector and then I move the e plus f vector so its tail is at the head of d, and this is the result. Now I display those two next to each other, and again you can see that it doesn't matter whether you do d plus e and then f or d plus e plus f. This vector is the same as this vector. Now, in this course, as we go further into the course, we will sometimes deal with vectors that do not lie in the plane of the page, but are instead coming out of the page or going into the page. Obviously, most of us are not great artists, and so how can we easily represent a vector that goes into the page or comes out of the page? We use two special symbols. For a vector going into the page, we use a circle with an X inside it. For a vector coming out of the page, we use a circle with a dot inside it. How do we remember which symbol corresponds to which kind of vector? We think of an arrow. If an arrow is coming out of the page towards you, the first thing you see is the tip of the arrow, thus the dot. If an arrow is heading away from you, what you see heading away from you are the feathers of the arrow, and thus the X. Now we come to an important conceptual point about vectors. As the title says, vectors are driving directions. It doesn't matter how you get there as long as you get there. So first let me pose this question. In which of these two cases is C equal to A plus B? All right, notice that A and B are the same in both cases, but in one case C goes like this, and the other case C goes like this. So in which case is C equal to A plus B? Here's a bit of a hint. I've marked the 3 points O, P, and Q. Okay, think about this and also review what you've learned so far about vector addition, and pause the video and try and think of the answer yourself. And now we'll go on and discuss the answer. So notice that A goes from point O to point P. B goes from point P to point Q. If we do A plus B, the net effect is going from O to Q. True, we go through P, but that doesn't really matter. All that matters is that we start at O and we end at Q. In which of these two cases does the vector C have the same effect? We see that in this case, C goes from O to Q. But in this case, C goes from Q to O. This has the same effect as A plus B. This has the opposite effect of A plus B. And so in this case, we have C is equal to A plus B. In this case, we have C is equal to the negative of A plus B. Another way of writing that is that A plus B plus C, for this case, is 0. Okay, this is the 0 vector. Let's see how this statement makes sense. A plus B plus C, the net effect of these driving directions is to start at O, go to P, go to Q, come back to O. So the net effect is start at O, end at O. And so we have not gone anywhere. In other words, our final displacement is given by the 0 vector. So A plus B plus C is just 0. That is not true in this case. A plus B is equal to C. If we did A plus B plus C here, we would have to put the tail of C at the head of B, and that would take us further off, up and to the right. Here is a question. The question relates these three vectors: vector r1, vector r2, and this vector delta r. And the question basically asks, if I want to write delta r in terms of r1 and r2, what is the expression I need? So, just reading the question. Given in the picture are two position vectors at different times, r1 at time t1, r2 at time t2. Those are just details you don't need to pay too much attention to. And the change in position vector is delta r. How can we express delta r in terms of the other vectors? To help you out, I have marked the points O, M, and N. We are looking for an expression for delta r. The effect of delta r is to go from M to N. So think about this question. Which of these combinations has the same effect as delta r, taking you from M to N? Remember that all that matters is where you start and where you end. Where you go in between doesn't really matter. So look for the combination that starts at M and ends at N. This is the end of this video. I'll see you in the next one.